Alright, so let's pick up here at proposition 5.6 from TAP. Here it is, the Lie algebra, or frac G, of the general linear group over K. We'll denote by little glnk, and we're going to argue that it has to be the just n by n matrices over K, and essentially there's no restriction. So in particular, that means that the dimension of the Lie group, the matrix Lie group, GLnR, is n squared. The dimension of GLnC is parentheses 2n squared, or 4n squared. And the dimension of the general linear group over the quaternions, n by n quaternionic matrices, is 16n squared. Of course, this is the real dimension. I think without exception I talk about real dimension here. You could think about complex dimension or quaternionic dimension, but that'd be something else. All right, so anyway, so here we go. If we have a matrix A, we can look at this curve, I plus TA, and for t sufficiently small, that will be invertible. All right. On the other hand, gamma of 0 is I, and the velocity vector of the curve is A, where we're identifying, of course, making the usual identification we can, because the set of we're in a vector space context, so the full abstract tangent space, we don't have to make use of that. We can identify vectors with points essentially. Anyway, by the continuity of the determinant, we know, of course, that the determinant of the curve is close to, it's close to 1 for t close enough to 0. In other words, the curve falls in the general linear group, and consequently A appearing as the velocity of the curve is a element of the Lie algebra, or tangent space of the identity. That was our definition. All right, so as point sets, the n by n matrices over K is equal to glnk. So you're like, well, why do you need another notation for it? It's just that this emphasizes that it's a Lie algebra. All right. So that emphasizes the Lie structure of glnk and its connection to big GL. So we use big G for the Lie group and little g for the corresponding Lie algebra, and that's a notational theme that you'll see throughout this literature. Proposition 5.7. And so what we're doing now is we're going to look at the Lie algebra of your favorite basic matrix groups. We'll start with the unitary group here. Unitary group of order 1. Little u1 of u1 is just the span of I. All right. Now, that's a real subspace of complex numbers. So one-dimensional real subspace, obviously. So here's the deal. You consider a path, e to the it. Well, that has meets the identity, which is just 1 in the complex numbers at time 0, and it gives you a velocity vector of I at time 0 as well. That's the initial velocity of the curve. So that means that I is an element of the tangent space at the identity to u1, which is little u1. And so the span of I is a subset, but on the flip side, we can argue that that's everything, because if you take a curve, take any old path, in u1, all right, such that it goes through the identity, then, well, that gives you a of 0 is 1 and b of 0 is 0, of course. But on the flip side, because this curve is in u1, in the unitary group of order 1, that means that the modulus of this curve is fixed at 1. But the modulus is a squared plus b squared. And so if a is 1, then b must be 0. Anyway, a is as big as it can possibly be. Consequently, a is a local maximum, in fact, a global maximum. So what's that mean? That means a prime of 0 is 0, but what's that say? Well, that says that gamma prime of 0 is just proportional to I, right? So gamma prime of 0 is in the span of I, the real span of I, and we can conclude that the span of I is in fact the complete Lie algebra. I don't mean complete in the technical sense. I mean the total Lie algebra of the big U1. All right. This shows that the dimension of U1 is 1, which isn't terribly surprising because U1 is, after all, like a circle. And you can also identify the circle with the rotations in the plane, which is one-dimensional. But anyway, moving along here. So proposition 5.8, the Lie algebra of the symplectic group of order 1 is little sp1. It's given by the span of ijk in the set of quaternions. So it's the sort of the span of the versors. Notice there's no 1 here. So it's a three-dimensional real subspace of the quaternions. That's what we're saying is the tangent space to the identity of the symplectic group of order 1. The argument is very similar to the one we just looked at. We look at these 3 particular curves, gamma 1, gamma 2, gamma 3, and respectively each one of these has a quaternionic norm, which is 1, which characterizes them being in the symplectic group of order 1, so they're curves in SP1, and moreover the initial velocities of said curves are ijk respective, which shows you that SP1 is a subset of the span of ijk. Right? So certainly SP1 has, I should say, ij and k are contained in SP1, right? And since SP1 is a vector space, I know that the sums of them are in there as well. Conversely, if you take a path in SP1, an arbitrary path, right, that goes through the origin, that means that a of 0 is 1, but b of 0 equals c of 0 equals d of 0 equals 0. But the important part here, of course, is that since a of 0 equal 1 is a maximum for a, it must follow that a prime of 0 is 0, which means that gamma prime of 0 is an arbitrary linear combination of the versors of I, j, and k, just like in our previous argument. So consequently, the symplectic Lie algebra SP1, little sp1, is in fact the span of ijk. It's three-dimensional. There you have it. Our next theorem from TAP, so I'm just giving you the best of here. He has additional commentary, and like I said, read his book, you'll get more. So theorem 5.9, if you have k, the reals of the complexes, the Lie algebra, little SLNK of the matrix groups, the special linear group SLNK, is given by little SLNK, and it's the set of traceless matrices in the n by n matrices over k. So the dimension of SLN over the reals is n squared minus 1, whereas the dimension of SLN over C is, I think it's 2n squared minus 1. I'm not sure if that's a typo or not, my logic here, and you tell me if I'm wrong, is that we start with the blank template of mn over C. That is, I'm pretty sure, 4n squared dimensional as a real vector space. I impose the traceless condition, but the traceless condition for a complex matrix is a pair of independent real equations. Thus I reduce the number of degrees of freedom by 2. So what I have is 2n squared minus 1. 2n squared. I think it should be 4. Oh man, I don't believe that. Well, here's what my gut is telling me. Because I had the dimension of GLNC being 4n squared, right? I think I have just that minus 2 real dimensions. I mean, this is the real dimension, of course, 4n squared. So my gut feeling here is that this should be 4n squared minus 2 because the traceless condition is 2 real equations. So, all right, the real part and the imaginary part. Now that said, here's the proof. So basically it relies on this deep lemma. Well, I mean, deep is in the eye of the beholder, I suppose, but at the very minimum, this is a fun lemma. So the derivative of the determinant of the curve is equal to the trace of the initial velocity of the curve. Now, evaluated times 0 there, of course. So if you have that, you can construct this curve into SLNK as follows. Because, I mean, get more to the point, the determinant is fixed to be 1, right? So this derivative works out to 0, which then gives us that the trace is 0. And there you have it, the traceless condition for the Lie algebra of big SLN. All right. Now you say, well, are you sure you can construct such a curve? Well, yeah. If we have a, you know, I mean, so that gives you one direction. We have to go the other direction as well, right? So suppose you have A and M, which is traceless. We'd like to show that this arises, that such an A arises as the velocity, the initial velocity to some curve, and that curve, of course, being in SLNK. So the trick is just to we use our usual thing, gamma of t is I plus dA. Of course, that goes through the identity, and it has gamma prime of 0 being A. That's no guarantee that's going to be in SLN just yet. So what you do is you do this little trick here. You define yet another curve, alpha of t, divide the first row by the determinant of the gamma, and so this one, it's going to be what? It's basically just, I say 1 over this times that. I don't think that's, I don't believe in this equality here, guys. No. Let me just scratch that out. I don't believe that. That's not true. Yeah. That would be true if I put a determinant around things, all right? Which is what I'm thinking about there. I'm thinking about taking a determinant, but I'm not writing it. I'm like the calculus student who writes x squared equals 2x. And it's like, what are you doing? Well, you're differentiating, right? But you didn't write it. Here I was determinating. That's not a word. I was taking the determinant, but I wasn't writing it, right? Anyway, so the determinant of alpha of t is equal to 1 because it ends up being the determinant of gamma of t divided by the determinant of gamma t, which is 1. Because gamma, for t sufficiently small, we're an invertible image of gamma. All right, so we don't have division by 0. Anyway, there you have it. You got the curve alpha of t is in SLNK, and it takes as its initial velocity this traceless matrix A. Okay, I mean, I guess technically speaking, alpha doesn't take A as its initial velocity. It takes something close to A, but it's pretty much arbitrary traceless matrix, so there you go. All right, there's a little bit of fine print there. I'm going to skedaddle over here. Now, excuse me, the lemma. I'm going to give a proof a little bit different than the one in TAP, because this is one of my favorite bits of math, so I'll show you how, yet again, the levi-civita symbol is the hero. I mean, the thing is, if you have the courage to work with the levi-civita symbol and just do calculus, you can do a lot. And it seems like a lot of people are afraid of it, and that's unfortunate because really if you just have a little perseverance and the willingness to use the levi-civita symbol formula for the determinant, you can really go a long ways with a minimum of cleverness. So the argument I'm about to show you is pretty much just brute force, right? But here it is. So I can calculate the determinant by this summation, which is explicitly multilinear in the either columns or rows of gamma, however you want to look at it. Doesn't really matter. So because the determinant of the matrix is the determinant of the transpose, right? So it just so happens that I can be a little bit nonchalant about that. Of course, we could be precise. I mean, what is this? 1 is fixed, I1 is varying. So what are you doing? You're going up and down. These are the first column. This is the second column. This is the nth column's components. Completely anti-symmetrized sum. So you differentiate that thing, and then you use the product rule n-fold times, right? And each time you have one derivative, and everything else just rides along. Over here is the anti-symmetric symbol with a multi-index for brevity. Now, we're assuming that gamma of 0 is the identity. That means that each column, right, the jth column, in fact, only has non-zero entry in the jth entry. In other words, the columns are the standard basis. Thus, when you put that up in the product rule, you get all these lovely Kronecker deltas, and those make just about all the sums go away, except for one, and each one of the sum ands. All right, so you end up with this here. You got epsilon I1, 2, 3n, epsilon 1, I2, 3, da 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 n, and so forth. There's only one free variable in each one of these levi-civita symbols left over. But then again, these sums are kind of also very silly because the antisymmetric symbol is only non-zero if the indices are distinct. But there's only one distinct index left to use here, 1. The only thing I can put in here and not have 0 is 2, otherwise I'd have a repeat. If I put 1 here, I've got 1, 1, which is 0. Or I've got 3, 3, which is 0, etc., etc. This forces this sum, the only thing that's non-trivial is when you have I sub n equal to n. So these nasty looking summations in fact just reduce to this. Gamma 1, 1, gamma 2, 2, gamma n, n differentiated at time 0 evaluated. And then out here you've got this harmless little epsilon 1, 2, da 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 n, which is by definition 1. So there you have it. This is the trace of the determinant. This is the trace of gamma prime of 0, but trace is linear, so you can pull the differentiation outside. And there it is, the lemma. Now the proof in tap, he uses another technique based on the cofactor expansion. Oftentimes you'll see proofs of this identity back at the level of traces and exponentials and such. Well, anyway, I'm sure we'll get back to it eventually. A lot of books that you'll see, especially in physics, they'll assume diagonalizability when they're proving something like this, and that really rubs me the wrong way. You know, not all matrices are diagonalizable, but whatever. All right, so again, Tap uses this like really slick cofactor style argument, and you should buy Tap and look at it. All right. So with that, I'm gonna cut this off right here, and then pick it up again with how we can think about the algebras as vectors, vector fields rather.